Starting to record. Wait. No, lecture. Yeah.
I'd like to welcome you to this.
All right, that was our intro from the structure and interpretation of computer programs. One of the most legendary and inspirational computer science courses ever made, which is not about computer science. All right, so I'm back. We stopped last time at the successor function. Yeah, at the successor function. Let's open the console. Console. Wait a second. Where is the dev? CD into Haskell. CD into GSCI. Yeah, like this. Let's make it big. Maybe too big. All right. So the successor function. So that's the increment, right? So the successor one. Let's just read. The successor function takes anything that has a defined successor and returns that successor. Takes anything that has a defined successor and returns that successor. I don't understand. I even don't understand this. The successor function takes. The thing with learning Haskell is really doing what's the core idea of functional programming is actually applying functions. So what I see, sometimes I get too attached. I'm not sure the right word. It's like you end up looking more at the thing or like the value, and we're kind of used to manipulate the values in a really fast way in our head, and we don't really separate the functionality, like first do this, first do that, first do this. um, so the successor function takes anything. So a successor function is a function that takes an argument of some type. Okay, we're still not doing types, right? We're still pretty low. We're not low, we're at the base. We're just doing, numbers, which are basically values. We're not abstracting or not adding some kind of properties to the functions themselves, like some kind of meta rules for the rules. So we're just using, numbers. So this is pretty, basic, but still the successor function. So the successor, so let's write this. The successor function is a function that takes an argument. Let's write just the x, that takes anything, right? So we can just write an a. We could do an a, right? Or an x. We could do an x. I think, if you write the n, that's kind of a rule, not a real rule, but if the function is working with numbers, you just write an n. If the function could work with numbers and, letters like characters, then you do x. If it takes really anything, then you could do like a, I think. Or even p. P has also some kind of a meaning. But yeah, okay, let's get back. So the successor function takes anything that has a defined successor and returns that successor. What has a defined successor? Where did we define it? Or maybe like the number 2 has a defined successor, which is 3, and then it returns that successor. But maybe I just don't. The successor function takes anything. Like in situations like this, you can actually use, ChatGPT You know, like, okay, we know what's a successor. I know what it is, but still this function, it's really important to know what you mean with the words in functional programming. Um, this is gonna work or what? No, it's not working. Yes. So the successor function, short for successor, kind of slowish. The successor function, short for successor, is a concept primarily used in mathematics and computer science to describe a function that takes an input value and returns the next value in a sequence according to a specific rule. All right. This function is often defined for data types or structures where a clear next element can be determined. Yeah, a clear next element. I guess this successor function is maybe it's used for total orders. Total order is a kind of a mathematical order that where it's like if you line people by height. If you have like 10 people and you can line them by height, and so with any type of, so this is an example with people, but you kind of know you can line them by height. And the most, okay, but the basic example would be, of course, with numbers. If I have 10 numbers, I can line them up. I know I can say this one is smaller than the next one. Well, I cannot do that with university classes. Like if I take math 1 and math 2, and then to take math 1 and math 2, I can take advanced math. So I can line them up. But math 1 has nothing to do with playing drums, you know, or I don't know, statistics. You know, it's like some of these classes you have to do before you take the next one, but some of the classes are not related. So that's kind of a different kind of or order. I think that's what we call a partial one, you know, where you cannot line up everything what you have in a collection of things that you have. Yeah, so in programming, the implementation of suc function depends on the type of the values it handles. Here are some examples: integers, characters, and numerations. Yeah, but I'm confused if that has a defined successor. Yeah. Wait, let's see how does. I'm confused with the wording of this sentence. Like, how do I anything that has a defined, like the anything that has a defined successor? Uh, can indeed be a bit tricky to unpack because it hinges on the understanding. Ah, it hinges on the understanding of what anything that has a defined successor means. So the suc function, this refers to a function commonly used in programming in mathematics, right? Takes anything. So that's the one that it takes, like an x. This part means that the function can accept various types of inputs. Anything. Well, it's not true, right? I mean, it takes anything in, but it depends. That has a defined successor. So it has, it's maybe it could sound confusing at first. This part that the function can accept various types of inputs. The nature of these inputs depends on the context in which the function is implemented. This might be strictly numerical, where, yeah, when it could include characters, days of the week, or other innumerable types. That has a defined successor. It can only be applied to values where a next item in a sequence is clearly defined and known. A successor in this context is the next logical item following the current one. Yes, for the number 1, the defined successor is 2. For the letter A, the defined successor could be B. For Monday, the defined successor would be Tuesday. Yeah. Or like an interesting example, for 12, the defined successor could be 1, right? Yeah, in a clock. If you look at a clock, the defined successor after 12 is 1 because a clock is a monoid. I can't wait to get to that, right? Um, yeah, okay, let's just, it's, I don't know, I guess it's helpful to run through things like this. Maybe, the successor function takes anything that has a defined successor and returns that successor. And in Haskell, when you learn it, a lot of the wording and the code, or even the paragraphs themselves, have this kind of structure. So the something something that takes something and returns something, or it takes and of some type of this and returns something of a type this that is defined by something something and something, right? Later, when it abstracts, this will be important, yeah, when it starts to abstract and talk about properties of things that the function is abstracting, like, or the function that calls other functions. We're not doing this now, we're just doing with values, but later when we have like a function that calls another function that takes another argument of this type and returns some kind of a function that does something else and does something else, I think it's important to really get the basics right. And when you learn like what a function does, that you can put it into words. That's what I find it. Maybe I'm stuck with that a bit, trying to make my words clear. But like, I think it's like with Graham Hutton, Hutton. Wait a second. Program. Yeah, I bought this book, although this is a pirated copy because I need a PDF. But Graham Hutton, if you're watching, I bought this book and it's coming. It's in mail. It's on way. I can prove it. I can prove it. Wait, I should prove it. No, I don't want to waste time. Wait, yes, look, returns. No, I have to sign in. Ugh. No, okay, right. Okay, well, anyway. In function, yeah, this thing, a function. Ugh. A function is a mapping that takes one or more arguments and produces a single result. So this is like the first level, right? And I'm talking now about this a bit more because I also want to make it clear to myself, and it's important. Like, so it's almost like zooming in and out. We are used to going from here to there, I guess, in like a value here and a value there and a value there. But in functional programming, I guess it's more like it's cool, like more space because it's total. The functions are total. So when they do more things, it's like you go inside, you zoom in and then you zoom out. Like a function is a mapping that takes one or more arguments and produces a single result. That's clear. And is defined. So now you go in, now you go into the body. The body, and because the head is this, it takes one or more arguments. That's the head. Right? The input of the function, that's the head. And then the body is defined. So now we go inside of the body, like spore drive, and go engage into the body using the equation. And it's defined using an equation. So that's the equation that gives a name for the function, a name for each of these arguments, and a body that specifies how the result can be calculated in terms of the arguments, that gives a name for the function. Oh, now it goes in, but it's still out. You see, like it went in, but then it's looking at the function from inside. So it's defined using an equation that gives a name for the function. So that's like the total name of the function. Let's say identity function or add function. Then it describes it again. Okay, first it said that takes one or more arguments, and now it says a name for each of its arguments and a body. Now it goes inside of the body that specifies how the result can be calculated in terms of the arguments. So it's like, you know, if you give me something, I will double it, right? So a name for each of its arguments. I guess we will have a name for like a double function, but like you give me a number and the body, and how it will be calculated, it will be I take that number and I add it to itself, and then I get a double. Oh, now it's talking about double. For example, I didn't see this. A function double that takes a number x as its argument and produces the result x plus x. So this is kind of, yeah, it's clear, but the wording, I think it's important, and Graham Hutton really talks like a compiler. You know, you should definitely check. You should definitely check on YouTube. There is a whole course that, I mean, it's, I think it was opened up this year or something. Graham Hutton is really nice. Graham Hutton. So he has yeah, he has a this thing, functional programming in Haskell. So there's advanced. There's also advanced. So I'd also like to go through these things. But the way he talks, it might be hard. Like I would sometimes, you know, listen to him, and it's almost like he's reading from a book when he talks, and the book itself is a Haskell program. So he's not like me doing that. Oh, you know, but yeah. So it's almost like sometimes I would. I remember I would like. I would read this out loud and walk in the park and just repeat this. Yeah. So let's move on. The suck function. Wait. The function min and max takes two things that can be put in order like integers. Min returns the one that's lesser, and max returns the one that's greater. See for yourself. GSCI. Wait. I have in public. Wait. Wait. Min. Do we have already min? Oh, I didn't know that. I thought we have to define min. See for yourself. Like min is the minimum. Min 2 and 3. We have min already. What's the type of min? Ah, order A. A. So a min is some type of a function that belongs to a class. This is some kind of a class, or like, yeah, I think this is the class, and the instance of this class is the num type, is the num class. So the num A class, right? As in, let's see that, yeah, wait, let's look at the type of a number. Yeah, so you see 4 belongs to a num class, and it's an belongs to a num class, and it's just an A, right? So that's like 4. If I do, can I do like a type of a 4 plus 4? Oh, nice. 4 plus 4 is such that, you see, this also has a word. I think it's such that, or has a type, right? Has a type, or belongs to an, you see, I also get confused. Num class, or it belongs to a num A, and this also thing has a word. I'll have to check these words. And you read them and then you forget them? Oh my. So min 2 and 3. No, we have min 9 and 10. Min 9 and 10 is 9. But how is min defined? This is also, so min, I think there is minimum. Minimum 9 and 10. Oh. For all foldable. I think minimum works on lists. Minimum, let's see, 1, 4, 3, 17, 5. Oh yeah, minimum works on lists. And min works on numbers, but like I think 2 numbers, right? Min 2 and 3. Let's try min 2, 3, 5. No, it won't work. So min is defined as Min is a function that takes an x and outputs a function that takes a y and compares them, right? If x is smaller than y, then it's x because we want the minimum number. Else just if it's not true, if x is not smaller than y, then just okay, then probably y is smaller than x, right? Will this work? Min, oh, I didn't name it. Wait, let's see. Min mine. Min mine. No, mine min. My min. So let's see if it works. My min 3 and 4. It does. My min. Oh, my man. My man. My min is so it's a function that takes another function and that then does this. If x is smaller than y, then x, else y. Right? So probably the same would be for max. My max is what? It's a function that takes an argument. It's a function that takes another function. Yeah, we're talking about currying now. So it's a function that takes another function and that takes, and it does if x is, no, now it'll be if x is bigger than y, than x, because we want the maximum. Otherwise, it's probably y. So my max is 3 and 4, gonna give me 4. So we can use 3 numbers, except if we apply it more times, right? So like my man 3 and 7 and then 198. So now we can apply it to 3 numbers. Yeah. And let's try my max. My max 198, 5 and 7. So it should output 198, 198. So it works. All right. Min 9 and 10, max 100 and 101. Am I recording? Okay, I'm recording. Max function application. So calling a function. Yeah, it's like you can say calling a function or function application. I think this is better. Better. Function application or calling a function, because who's calling a function? Another function. Function application, calling a function by putting a space after it and then typing out the parameters. So yes, the space after it denotes function application, right? So the emptiness of space denotes the function application, which is really cool, right? So because it's the most used, there is a mathematical reason for it. It's like 3 times 3. That's like function application, right? So, but yes, because this is only for numbers 3 times 3, right? You can write apple times apple, right? No instance for num string. We don't have a num string. So but it kind of, this is applying it. I don't, you see, I don't know the right word, but if I think this is the reason, yeah. So if we move this sign and we just leave an empty space, and then it's like F and A. This was a bad explanation. What that means for us is that these two statements are equivalent. Function application, calling a function by putting a space after it and then typing out the parameters, has the highest precedence of them all. Oh, what that means for us is that these two statements are equivalent. So function application, yeah, has the highest one. So if I write f a b, that is the same as that is actually f a and then b, right? Like we write like this, but this is actually what happens. F is applied to a, and then the result of this, whatever is applied to b, right? That's the idea. What statement? Suc9 plus max5 4 plus 1. Suc9, yeah, so yeah. Because this is function application and this is function application. Right? Not this. This. So successor of 9 is 10 plus max of this is max of 5 and 4, right? So 4 will not be, it will not do 4 plus 1, but max 5 4 has, okay, so the successor of 9 is 10 plus max of 5 and 4 is 5. 5 plus 1 is 6. 6 plus 10 is 16, right? We get 16. However, if you wanted to get the successor of the product of numbers 9 and 10, we couldn't write successor 9 times 10 because that would get the successor of 9, which would then be multiplied by 10. So it's the same thing. We'd have to write successor 9 times 10 to get 91. So with the parentheses, you can, you can say what you mean. Like if I write suc, wait, suc is a type, right? Wait, suc is a, yeah, suc is already defined. And t inc, did I define inc? No, I didn't. The successor, so the successor probably works on characters, right? The successor of a, wait, of a, that's b, yeah, right. The successor of apple, do we have that? No, we don't have this. The successor of apple is a pear. It's true. No, the successor of 9 times 10 is 100 because the successor of 9. So the function application has the highest, it's the most important, right? Like because it's the first class, right? The successor of 9 is 10. 10 times 10 is 100, right? And if you wanted to take the successor like this, and 9 times 10, 91. Yeah, it's, you see, it's applied like 9 times 10 is 90. Successor of 90 is 91. All right, it takes now. Okay, right. So if a function takes two parameters, we can also call it as an infix function by surrounding it with backticks. For instance, the div function, the divide, I guess. Div takes two integers and does integral division between them. I never what's the integral division? Oh, is it like without the remainder? Doing div 9210 results in a 9. So div, probably div and 6 will be what? 1. Oh, because there is 1 6 that goes into 10. I guess like that. Yeah, div 10 6 is 1. So that means that div 20 and 11 will be also 1. And div 30 and 16 will be 1. And div 40 and what would be the number? 21. Yeah, is 1. And div 50 and 26 is 1. 6, 11, 16, 21, 26. This looks kind of like a nice linear function. I don't know. So we can do like backticks. So 10 and wait, backticks are here. Yeah, I know. Div 10, div 6 is 1. All right. For instance, the div function takes two integers and does integral division between them. Doing div 9210 results in a 9. But when we call it like that, there may be some confusion as to which number is doing the division and which one is being divided. So we can call it as an infix function by doing 92 div 10, and suddenly it's much clearer. What's clear? There may be some confusion as to which number is doing the division. Oh, I see. And which one is being divided. Which one is being divided? So we can call it as an infix function. 92 is divided by 10. Oh, that's it too. It's like 92 is being divided by 10, right? It's being divided by 10. Divided 92 and 10. Yeah, that's why. Okay, that makes sense. 92 is being divided by 10. Lots of people who come from imperative languages tend to stick to the notion that parentheses should denote function application. Yeah. I think also from math in school. No, I think. For example, in C, you use parentheses to call functions like foo and bar and baz3, haha, but that's different. Yeah, okay, people are used to that, but these are not mathematical functions. So this is not just about, yeah, I don't know. The node function application, I don't think they would use the word function application. So the parentheses should denote function application. Well, they're used to this, but I don't think they would call it the imperative programmers. They're like applying a function. They would just like, I think they would say call something. Like call, you know? Like we said, spaces are used for function. Like we said, spaces are used for function application in Haskell. So those functions in Haskell will be foo, bar1, and baz3, haha. So if you see something like bar3, it doesn't mean that bar is called with bar. And 3 as parameters. All right, yeah, so bar is called with bar and 3. It means that we first call the function bar with 3 as the parameter to get some number, and then we call bar again with that number. In C, that would be something like bar3. So I guess this is for people that are kind of a little bit familiar with imperative programming or have some, yeah. Like I don't think like this because I don't think like this because, but it makes sense. Yeah, kind of this, and inside foo, and inside we're gonna, yeah, I'm not sure how it's in real life. Like, yeah. Okay. Let me tell. Hi. Do you want to say hi? Hi. She's her name is Dandelion. That's a translation of her name. Her Dandelion means maslačak on Croatian. Dandelion, yeah, sounds like, but Dandelion sounds cool. Baby's first functions. All right, we get to baby's first functions. Baby steps, right? Baby steps. In the previous section, we got a basic feel for calling functions. Yeah. Now let's try making our own. Open up your favorite text editor and punch in this function that takes a number and multiplies it by 2. And punch in this function that takes a number, and also we have to, so we can, oh, bye-bye, REPL. Wait, so let's open up text editor. I use Helix because it has a cool name. Open up your favorite text editor and punch in this function that takes a number and multiplies it by 2. Do we name the editor somehow? Oh, save this. I'll be later. Okay. So hx baby.hs. Wait, can I just open up a file like this? Now it's a scratch. All right. In the previous section, double me. All right. Double me x is x plus x. All right. Functions are defined in a similar way that they are called. Oh, functions are defined in a similar way that they are called. Yeah, I don't understand this sentence. I understand what he wants to say, but are defined in a similar way. Maybe I don't understand what he wants to say. Are defined in a similar way that they are called. So does that mean you call it in a similar way? What does this mean? What does this mean? What is this? What do you mean? Ram, hi. Functions are defined in a similar way. What does this mean? Let's this mean? I'm like the wording is kind of not clear. I know what he means, but what's this wording about? Sometimes I write like this to ChatGPT, and the phrase functions are defined in a similar way that are called in Haskell or other functional programming languages generally means that the syntax. ChatGPT is sometimes really slow like this. I don't know why. Means that the syntax used to define functions is very similar to the syntax used when calling them. Definition against calling. Okay. Stop. When you define a function, yeah, I wish it wouldn't just always pull me down. When you define a function in Haskell, you typically specify the function name, followed by its parameters, then an equal sign, and the expression that forms the function's body. Yeah, okay, that's the add xy is x plus y. When you call this function, you use the function name followed by its arguments in a similar manner. Oh, so you do like add 3, 5. I'm calling it. It means I'm applying the arguments. In Haskell programming from First Principles, another book I bought, yeah, he was saying like when the values, like before the arguments are applied, the before like here, like before the arguments themselves are applied, these are called the parameters of the function. So these are the parameters, and when the values like we put inside, like let's say 3 and 5 are applied, then these are called the arguments. Well, I guess that's a nice separation, but I didn't hear this. I don't think Graham Hutton said that. I don't know. When you call this function, you use the function name followed by its arguments in a similar manner. Notice how the structure of the function calls mirrors the structure of the function definition. Yeah, only because add xy, add 3, 5. Mirrors the structure of the function definition. Add xy in the definition corresponds to add 3, 5. All right. Well, now it makes sense, yeah. Functions are defined in a similar way that they are called. So double me x is same as double me 5. Okay, double me 5. The function name is followed by parameters separated by spaces. But when defining functions, there's a equality sign, and after that we define what the function does. Save this as baby.h. Right, baby.h. Right, let's quit. You should definitely check out Helix. It's cool. Baby.h or something. Now navigate to where it's saved and run GACI from there. Once inside GACI, do load baby. Now that, oh, so we don't have to write the HS. Now that our script is loaded, we can play with the function that we defined. lbaby, all right, GACI, lbaby. Okay, one module loaded. Double me 9. Double me 8. Okay, double me 9. Double me 9. Oh, no, double me 9. Should work now. 36. Double me 9 is 18, and double me 9 is called now. 18 is now called. You see, 18 double me now is applied to the result of the double me 9. So double me 9 is a function that as an argument takes the number 9 and returns the result, which is double me, so which is 9 plus 9, which is 18. Then double me double me double me is a function that get passed into double me, or like double me is applied to the result of the double me 9. Then we get 36. Double me, it works also on floating point numbers, 8.3, double me 8.3, 16.6. Because plus works on integers as well as on floating point numbers, anything that can be considered a number, really, anything that can be considered a number. Plus works on integers, okay? Does it work on imaginary numbers? I don't know. Our function also works on any number. Let's make a function that takes two numbers and multiplies each by 2 and then adds them together. Double us. So double us xy. Do we have to go back? Yeah, let's go back to our baby. We don't have a type here yet. He's not doing the types. I guess the type would be, what would be a type? Double me, is a type, has a type of what? Num A. I guess it's a class. Oh, this is nice. We have num A. Expected a type, but num A is a constraint. Or we could say like double me A. No, like this A. And no. Double me. Wait, we could do like this. A. Do we do like this? Double me A. Is A? Is this true? Double me A? Would this work? No, I don't think it will work. Come on, show me what parses error on input. Double me A takes an argument A and returns an A. Is this? No, it's not true. Let's do double me num A and A like this. No. Like this? No. See, I don't know. Wait. Let's quit. GACI, load double me. No, it's baby. Load baby. What's the type of baby? What's the type of baby? No, the baby's name of the file. What's the type of double me? Ah, the double. It's the double. Is cool, right? So the double me is an instance. The double me is a function that is an instance of the num A class. It's part of the num A class. And how do you read this? I don't know. A. Yeah, I can see what this means, but I still don't, can't put this into the right words. So double me, num A. Yeah, now it makes sense. So the same would be with add. Add would be the same, I think. Add would just be also num A and and A, because add takes two numbers. So here it takes one. It takes one, which is an A, and then it doubles it. So the add will have like A, and then another A as the result. It's a function that takes, yeah. Okay, let's do double us. Okay, let's do double us hx baby.hs and double us. Double us will take an x and a y, possibly incorrect. Let me type. Oh, oh wow, I can't type. This is kind of, I appreciate this. Is it because I'm, oh, that's why, yeah. Interesting. Yeah, if I really zoom in, then it obscures what I'm typing. Type. Oh, this is not really practical, and I was just saying like use Helix. Like, why is this? Can I change this? Wait, let me make a print screen. I'll make a prick a prick a prick screen, and I'll just, yeah, I'll just actually, maybe I'll ask this in Helix. Helix save as Helix Helix hx parsing hxq, I don't know, hxq. I'll check with the, wait a second, let's see. You know what, this is also great. Someone search Frickler. Wait, Helix, I joined. Wait, invite, public space. Does anyone use Helix on Mac? I'm failing to use. So if you have a problem like this, let's check this. Double us, possibly. Yeah. Is can one like change where the error comes, because kind of obscures what I'm typing. I'm checking now actually in the matrix channel, and because it's important to do these things, you know, otherwise you don't do them. Helix, open. Obscures what I'm typing. Yeah. Yeah, let's see. Okay. So double us xy. Wait. Yeah. What's this? Oh, I was doing something here. Exit. Okay. You see, I don't, xy is x times 2 plus y times 2. Simple. All right. Let's save. Let's go to GCI. Load baby. Baby, and wait, what did I do? Double us. Double us. What is it going to do? Let's do 3 and 4. So it doubles the 3 and it doubles the 4, and then it adds them. X plus 2 plus y plus 2. Yeah, simple. We could use We could have also double it. Let's try the sum of squares. That was in the structure of interpretation, like the square of x, the square of a number, the square of n is n times, oh, what did I do? Okay, n times n. So now we have a square of 2 is 4. Square of 8 of 56 is, wow. So sum of squares is, oh, this is simple, yeah. Sum of squares x and y is square x plus square y. Yeah, sum of square 3 and 4 is 25. All right. Yeah, that's nice. Simple. We could have also defined it as double as xy is x plus y plus y. Testing it out produces pretty predictable results. Remember to append this function to the double.hs, save it, and then do load baby. Inside GACI, double us. As expected, you can call your own functions from other functions that you made. With that in mind, we could redefine double us like this. Double us xy is double me x plus double me y. So yeah, now we are coming to the core idea. We're coming to the core idea of functional programming is that, well, we just did this here. We defined square and then we define sum of squares. Instead of writing sum of squares, xy is x times x plus y times y. We used the function that we defined and we called it. We called it and then we applied it to x and square y, right? So we are kind of building it. We are building our complexity for like from small parts, and we can build complex things. Now I'm trying to remember when Brian Beckman said, building complexity is, yeah, there's this talk I also want to cover from Brian Beckman. What is a monad? This is a great talk that I watch from time to time. Yeah, it was saying something about building blocks. It's the way to control complexity. What's the way to control complexity? I don't remember. Yeah. As expected, you can call your own functions from other functions that you made. With that in mind, we could redefine double us like this. So now he's doing double us xy is double me x plus double me y. Another interesting thing is that you can define double just like this. Double x is a lambda x. We're going to do the lambdas, right? I like lambdas because I can use this thing here. No. Can use this. Double is lambda x x times 2, right? But yeah, one example that Graham Hutton used is when you call a double, actually let's show it like yeah, let's show it like this, hx double, right? So if you write double 2, right, what's gonna happen? He really showed that, or I can just show it. I can show it because it's really interesting. Yeah. This thing, wait, let me. So double 3, applying double. This is important, right? So you separate it. Like double 3, you immediately think, oh, that's 6. But it's not. Like double 3, okay, applying double. What does it mean, applying double? Applying is doing 3 plus 3. So it's almost like you don't add it yet. You're applying the double and you kind of like do the double. You see? Like I would immediately say, okay, if I do a double, it's 6. But no, you're applying the double, which means you're just going to do 3 and 3. And then you're applying plus. So you're not applying double, you're applying plus. So double 3 is plus 3 plus 3, and then you're applying plus 6. So it's almost like you have 2 steps to get 6. You usually we say, oh, that's just one step, double 3 is 6, because we do a lot of things, in our mind, because, we're fast like that. So double 3 is 3 plus 3 and 6. So similarly, the result of the nested application double 2, in which the function double is applied twice, can be calculated as follows. Now check this out. Double applied to double 2, applying the inner double. So this means that there are 2 ways like you could apply this. You could first apply the inner double, or you could do the outer double. So like you have double 2. So you could have double 2 and double 2 and then do the calculation, or you can do double 2 and you start with double 2, like here, right? Double 2, double 2 plus 2, as before, applying plus, you get 4, then we have double 4. Now you're applying the outer double, right? He didn't write the outer double because there is no more outer double, but that's like the outer double from before. Double 4, applying double, 4 plus 4, applying plus 8. This looks like basic stuff, but this is this is important because later when like complex things come, it's I think then thinking becomes smoother, right? If you get the basics. Wonderful thing about functional programming, it's almost like nothing gets wasted. Everything what you learn somehow builds up. And it's important it's important to know how to put your thoughts into words as soon as possible. As soon as possible. I mean, if you know how to put your thoughts into words and build on that, I think some of the understandings can unravel, like unfold by itself, later, because you are led, you can be led with these words. I don't know if this makes sense. 4 plus 4, applying it 8. Okay, alternatively, the same result can also be calculated by starting with the outer application of the function double. So not with the outer double. Let's start with the outer double, right? But you can say like, starting with the outer application, because the point is there are 2 applications. There are applications, right? So the outer application is the double. Sometimes we say like, let's start with the double. Which double? With the outer double. Let's start with the application of the outer double rather than the inner. So double 2, applying the outer double 2 plus double 2. So it's, I really wish, I hope it's like a secret wish. I think it would be cooler even if you could like see these things in your mind. No, if you could write a program that would kind of visualize these things. Wait, Chris Doan did something like this. Chris Doan. Doney? I don't know how, but I remember that. Chris Doan. Let's Haskell evaluation show. My Haskell tooling wish list. Chris Doan. I remember he was like a Chris Doan. Oh, on compiling to Java evaluation. Yeah, I think he's like a cool. Look at him. He's nice. Haskell face. This is a Haskell face. Like Simon. Yeah, I guess after a lot of Haskell programming, you get this face. I think it's true. You get this face, right? Even Stephen Deal, I think Deal has that. Wait. How do you show? I think is evaluation show steps, debugging, view reduction steps in Haskell. That would be nice. Is there a way to view the reduction steps? Trace the recursive calls. Yes. A lot of things, trace lambda. Yeah. A lot of these things You could try insert and debug trace trace in places you want to trace, but this has a tendency of producing wildly out of order input. Gives the result. No. No, I thought like something visual. Helium. Vacuum. Yeah, it will be, I think it will be helpful. Like you can see the evaluation. Wow, what's this? Ooh, let's see this. Vacuum, view, linking. All right. What's this? View 1 to 5. Oh, this is a whole list. Look at this. 1 to 5, zip, 1. Hello? No, not like this. No, 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 no. Thank you, but no. I mean to see like evaluation steps. Wow, can ChatGPT do that? Double two. Okay, show me in code the evaluation steps, which the evaluation steps, the expansion of how the evaluation is going with this function application. Double x, double two. This is Haskell. Can ChatGPT do that? We first must define double x. Now let's walk through this step by step. No, I could maybe, oh yeah, wait. Copy text. Oh. Do it like this. This is nice with ChatGPT. I think if you can, certainly to expand on the evaluation of double two in the style you've shown, let's assume. Why is it so slow today? Sometimes like if the chat is long, but it's not a long chat, it gets slow and I have to open a new chat. Applying the outer double. No, this is too slow. Apply the outer double. Ah, horrible. Double us. Second double. Maybe if I then give it. Yeah. Anyway, it would be nice to write a program that would do this, like double two, you know, and then you even in real time, and then you could. I don't know how that would work with more complicated functions, because later when the functions like this, now we just have two, but later is going to be this is a function and it will take as an input another function, so it will get more complex. So maybe it would be nice, I don't know if someone is doing on that, to have like to see really what's going on. Double two, applying the first double. Okay, I'm applying the outer double, right? So now you double the double two, 2 plus 2. But now you see applying the first double. Now you start from this one, 2 plus 2 plus double 2. Applying the first plus. It's 4 plus double 2. Applying the double, 4 plus 2 plus 2. Now this one, applying the second plus. But I guess there is a third way, I think. You could do 2 plus 2 plus, and now you could expand this. So then you will get 2 plus 2 plus 2 plus 2. You see, there are more ways. And Graham Hutton, I think he says even like, are there more ways that you do this? So you see, this approach requires 2 more steps. So you see, anyway, it's kind of an interesting thing to really go through these things like this, applying the outer double, because you almost skip some of these steps. when you do it in your mind, because you just do, okay, double 2 is 4, double 4 is 8. Voila, I'm done. But it's not like that, right? I think this becomes important now, may not seem important, but becomes important later. Will some of these steps become like real properties that have some kind of a sequence? Let's get back to the book. Double us, xy, double me x plus double me y. Okay, this is a very simple example of a common pattern you will see throughout Haskell, making basic functions that are obviously correct, obviously, right? And then combining them into more complex functions. This way you also avoid repetition. What if some mathematicians figured out that 2 is actually 3 and you had to change your program? You could just redefine double me to be x plus x plus x. And since double us calls double me, it would automatically work in this strange new world where 2 is 3. Right, so this is like the basic abstraction. You don't repeat yourself, you know. I guess that's the basic, yeah, okay. That's clear. Functions in Haskell don't have to be in any particular order, so it doesn't matter if you define double me first and then double us, or if you do it the other way around. I think that's functions in Haskell don't have to be in a particular order. Yeah, I think that's not true with guards or something. Yeah, but that will come later, yeah. Now we're going to make a function that multiplies a number by 2. But only if, let's see how long am I doing this. I don't want to make this too long. 1 hour and 6. This is too long. I'm sorry for making it so long. No, I wanted to do these shorter bits, like 45 minutes, like a class in school. Maybe I should have a bell, you know, at the end of the 45 minutes, like, trrr. Okay, sorry. Yeah. So actually, this would be a great place to stop, because this is like double small. Now here he introduces if then else. So these are more, this is a more kind of a control structure kind of a thing. If I give you this, then, or it's, this is almost like the Boolean conditional maybe, because it works on true and false. So if this is true, then you do this. Otherwise, or else, you do that. Yeah, we're going to do that next time. All right, this is a good place to stop. Wow, yeah, okay. All right, thanks. And I'll be going with this book until the end, and then I will move on. There was a comment in the first video about that I should continue after the book and do up to monad transformers, which sounds really cool. And then I'm going to do that because that's the like the breaking point, which is really cool. Thank you for that comment. I will do it. I will do it. And yeah, what else? Renzo Carbonara, the guy who wrote Type of Programming, which is another great book on Haskell that I'd love to cover too. But I started with this one first because, yeah, I don't know. And he shared the video on his Twitter, and people liked it. So yeah, I'm glad. You know, I mean, if it's beneficial for someone, I guess it is. You know. Anyway, thanks, and I'll keep up with this. This is interesting, and it's a great. Yeah, I'll stop with the platitudes. Okay, see you.